All right, let's take a look at an example and see how can we use what we just covered. Example, I have a machine. Its its mass is 25 kilograms, and it's placed on an elastic foundation. On an elastic foundation. A cosine function, right? A cosine force, let's put it this way, a cosine force with the magnitude with the magnitude of 25 newtons, right? This is going to be my F naught, right? Is applied to the machine That's it. Now it says a frequency sweep reveals that the maximum amplitude, or the maximum steady state amplitude, the maximum steady state amplitude of 13 millimeters occurs when the period of excitation is 0.22 seconds. Now I'm asked to find the equivalent stiffness, write the rest here, stiffness and damping ratio of the foundation. So the machine is sitting on some foundation. We do a frequency sweep, and we see that the maximum steady state amplitude is 13 millimeters, and we figure out at which specific time period, which is corresponding to a specific, obviously, frequency, at which frequency or time period the maximum amplitude occurs. Now, what we're asked to do is we are pretty much trying to, or this problem is trying to say, that we want to find the equivalent spring mass damper system for this machine sitting on this foundation, pretty much replacing this foundation with a set of a spring and damper. Right? From this information that we are provided, we need to find what would be the stiffness of the spring and the damping ratio for this system if you want to replace that foundation with a spring and damper for some, let's say, modeling purpose. All right, so let's see what we are given. We are given F naught, the amplitude of the force is 25 newtons. We are given the mass of the machine, right? It's 25 kilograms. We know the time period at which the maximum amplitude occurs is 0.22 seconds. And the maximum amplitude, I'll write it X max. It is 13 millimeters. These are the information we are given. Now, from the last two observations that I told you about from those plots, that we know When does the maximum occur? When we have a spring mass damper system and a harmonic force is exciting the system. We know when does that maximum occur, and we also know at which frequency it happens. So let's start with the maximum amplitude. Maximum amplitude. Well, we know that M max occurs at 2 zeta square root of 1 minus zeta squared. And also I know that if I go back to our notes 2 slides or 3 slides ago, that we know that this, let me change the color, this M, which is amplitude ratio or magnification factor or amplification factor, we said we can go with any of those names, is equal to x omega n squared over f naught. So when x is maximum, m is maximum, or when m is maximum, x is maximum. We said m is pretty much a representative of x. It's just a number that has no dimension. We just got rid of the dimension, or better to say, we made it dimensionless or non-dimensional. So this means that x max omega n squared over f naught is equal to 1 over 2 zeta square root of 1 minus zeta squared. Because m is the maximum, x is maximum. Now I know x max, this equation. I don't know omega n, I don't know f naught, but I can find those right, from the information I'm given. F naught, oh, it's pretty much just uppercase F naught over M. This case 25 over 25, so it's 1. What is natural frequency? Well, I know I can find natural frequency, or I can find the frequency too. Let's just go step by step. So I have F naught as 1. I'm just going to replace that here. I have X max is 13 millimeters. So let's just continue this. This becomes X max omega n squared is equal to 1 over 2 zeta square root of 1 minus zeta squared. X max is 13 millimeters. It's going to be 0.0013. Actually, it's going to be 13 divided by 1000. Keep it in SI. Omega n squared is equal to 1 over 2 zeta square root of 1 minus zeta squared. So I found this relationship between omega n and zeta. Let's just hold or keep this one here. This is one equation. I have one equation, two unknowns. I don't know the natural frequency. Right? I know omega because I know time period, but I don't know omega n. That time period is associated with the period at which the maximum occurs. So it's associated with the frequency at which the maximum amplitude occurs. Right? So let's use that information. Let's see how can we use that information. So knowing t, right? If I know t is equal to 0.22 seconds, I can get omega. And call this omega max, but the way I introduced that, you know, omega max means the omega at which the maximum occurs. So it's just going to be 2 pi over t. And that'll give you, if you do the math, you should get 28.6 rad per second. I got omega max too. Still, it's not that helpful. That equation I have, it has omega n and zeta in it, two unknowns. Neither of those I know. So what do I do next? Well, I don't know omega n, but I know omega. So R max, right? I introduced that in, I guess, the the one before the last observation from the plots. I know R max, well, would be omega max over omega n, which is equal to square root of 1 minus 2 zeta squared. If you go back to those observations, in observation number 4, I told you the maximum amplitude occurs when R is square root of 1 minus 2 zeta squared. Or the omega max would be equal to omega n square root of 1 minus 2 zeta squared. I started from the first statement here. And from there, obviously, omega. Let's write it in a better way. From there, I can get omega n. It would be omega over square root of 1 minus 2 zeta squared. And the value for omega, or in this case, omega max, I found it, right? 28.6. Now let's see what happened. Now I have another equation, equation number 2, that gives me a new relationship between omega n and zeta. So now I have two equations, two unknowns, right? I have the first one that I got from the fact that I knew what is the maximum amplitude of 13 millimeters. I got the second one from the fact that I knew what is the excitation at which the maximum occurred. I knew the value for that. Well, I didn't know the excitation frequency exactly, but I knew the time period associated with that excitation frequency. So I found that excitation frequency, omega max, from the time period. And then from what I know before, I knew the what would be the relationship, or what is R at maximum amplitude. Right. From there, I got omega max replaced with the number I got from time period. Now I have two equations, two unknowns, omega n and zeta. So all you need to do is to plug omega n from one to the other and solve for zeta. I have two equations, two unknowns, so the way you want to solve it is up to you. So what I will do is that I'll take the second equation. I take omega n from here, from this equation, and put it in the first equation, and then solve that for zeta. What happens is that you're going to end up having an equation for zeta that you have to find its root. So here is what I'm going to do. This becomes, if you replace the numbers, let me see if I can make it a little more clear. So this is 28.6 omega n from the second equation squared. The right side, I'm going to square the right side. So I'm going to get 28.6 squared, right, divided divided by 1 minus 2 zeta squared. Right? I can get rid of the square root sign. So I can write it this way. 28.6 squared over, well, I can get rid of square root now when I square both sides, or the whole fraction. Now, what else do I have? So I'm plugging this omega n to the first equation. I squared that. I have that point, or that 13 millimeters. Actually, I have to fix something here. That's not 13 millimeters. This is 1.3 millimeters. So sorry about that. That's the maximum amplitude is not 13 millimeters. Amplitude is 1.3 millimeters. So I'm going to fix it here too. It's 1.3 millimeters over 1,000 to convert it to meter. So moving things, you're going to get 0.0013 here, right? And the other side is the same, 2 zeta square root of 1 minus zeta squared. If I square both sides and move things around, I'm going to get an equation in this form. Zeta 4 minus zeta 2, zeta to 2, plus 0.118 is equal to 0. Now, this is a fourth order polynomial. right? It's first look, it's almost impossible to solve this. How can we solve a fourth order polynomial or find the roots for this equation? Right? It's not a quadratic equation that we can easily solve. But if you look at it closely, actually you can simplify this. Right? You can take zeta squared as some variable, let's say u in this case. It can be any variable. This becomes u squared minus u plus 0.118. Now it's a quadratic equation that you can actually find its roots. If you find the roots, right, you'll get two u values, and then for each u value, you can find the square root of that value to get a zeta. So if you do that, I'll give you the final result. You'll get two zeta. Zeta 1 would be 0.369, and zeta 2 would be 0.929. All right. So again, keep in mind from this equation, just don't get lost. From this equation, you get two roots. One of them is positive, one of them is negative. Probably the positive one, you can actually find the roots of that to get into zeta. So we get two zetas, zeta 1 and zeta 2. Now you might think that's the end of the story. Well, we got two zeta values, and these are the damping ratios. But that's not the end of the story. There is another step that you have to pay attention to. If you go back to those observations we made, observation number 4, I specifically mentioned that zeta should be between 0 and 1 over a square root of 2. Somewhere between 0 and 0.71. 1 over a square root of 2 is about 0.71. So that's the only range that you're going to get a maximum amplitude. If you're out of that range, if you're 0, well, there is no damping, so it's going to go to infinity. If it's greater than 0.71, I mentioned before, the maximum, there is no maximum. The line is in a way that plot, or the response in a way is in a way that there is no maximum point on it. So zeta should be within this range. Looking at these two zeta values you found, this does not work. It's out of that range. This is the only zeta value within that range. So you can put it this way: only zeta greater than 0, smaller than 1 over square root of 2. So the damping ratio for this system should be 0.369. So what we were asked to find? We were asked to find two things: equivalent of stiffness and damping ratio of the foundation. I found the damping ratio, so I got the damping ratio. The next step is to find the equivalent of stiffness. How do I do that? Well, I know omega n, right? I found that relationship between omega max and omega n. I'm going to go back here. Right here. I found this relationship. Equation number 2. Now in this equation, I have zeta. I can put zeta back. I have omega max. I can find omega n. Once I know omega n, I know omega n is the square root of k over m. So I can use that. I know the mass. I can use that to find the stiffness. All right. So let me do it this way. Omega n is equal to, let me add a line here. Just make sure that, again, you don't get lost. For stiffness, omega n would be 28.6, which is omega max, divided by square root of 1 minus 2 zeta value that I found now, 369 squared. If you do this math, you'll get 33.5 rad per second. Now you know omega n. Well, you should know this equation by very well by now. Omega n is the square root of k over m, natural frequency. So from there you can find k. Right? M omega n squared. What is the value of m? The value of m is given. It's 25 kilograms. So So that would be 25 kilograms times omega n squared, which is 33.5 squared. If you do this math, and if I did it correctly, hopefully I did, you should get 2.88 times 10 to 4 Newton per meter. So this is the value for stiffness. Stiffness. And this is damping ratio. So through running an experiment, what happened here is that by running an experiment on this machine sitting on this foundation, I got enough information by just observing the results that now I can replace this whole system, better to say, with a spring mass damper and do whatever I want to do. If I want to model this system, I want to model this behavior, I can use these values for stiffness and damping ratio and find the system response for any given external force. You can easily see how can sometimes easily by running few experiments, you can go from a real machine to a simple system we studied before. So there is a reason we are so focused on very simple systems like a spring mass damper or spring mass system, because there are so many cases, as I said before, you can easily find the equivalent spring mass damper to a real world problem, specific machine you want to study, and then use that to find a system response under any other condition.